All right. Good morning, everybody. Welcome back. I hope you had a good weekend, got some rest. So let's get ready for the week. So starting today, let me share with you some important announcements. So for this week, we will not have in-class assignment this coming Friday. So therefore, we will meet here on Zoom for regular lecture. This week, I will start the next chapter, which is chapter number 6. And in the chapter number 6, we are going to deal with thermochemistry. Okay, so those are our goals to cover in this chapter. We will start talking about forms of energy and energy transfer and also enthalpy. After that, we will move to Hess's law and then standard enthalpies of formation, followed by heating curves and calorimetry. And finally, we are going to discuss a little bit about fuels and food energetic values. Okay, so that's our outline for this chapter. It's a fairly short chapter with some very interesting concepts, and we will be able to discuss some things more related to day-to-day operations, for example, here fuels. Okay, so let's start then talking about thermodynamics. Thermodynamics is the science that studies the transformations of energy from one form into another. So in this chapter, we are going to focus on the energetic processes that happens during chemical reactions. There are only two forms of energy. The first one is called potential energy. Symbol is U. Potential energy is associated with the ability to produce work. And the second form of energy is called kinetics. Symbol is K. And kinetics energy is associated with movement. These two forms of energy can convert between themselves. So we may have at some point potential energy, and the potential energy is going to be used to produce kinetics energy. So let me show you a quick example here. So let me change to my other screen. Okay, so very good. So let's imagine here that we have a flat surface. And at some point we have uphill that stays flat and then gets here a downhill. Let's get a small body here at the bottom of the hill. If we move this small body all the way uphill, now this body is in a position that we call meta unstable. So that means any disturbance in the system will get this body out of the equilibrium position. Once we moved the body all the way up to the hill, we kind of charged this body with potential energy. See here that the body of the top at the top of the hill has the potential to go down the hill, therefore the ability to produce work. And once the body goes down the hill, all the potential energy now is transformed in movement, and at the bottom of the hill, this body has only kinetic energy. And then the symbol here is K. Okay, so potential energy can be transformed in kinetic energy and vice versa. Potential energy is always the energy that, if the system is disturbed, is going to be transformed in kinetic energy. Okay, so let's go back here really quick. Now I want to make clear the difference between heat and energy. Anybody can have energy, okay? And basically energy is going to be a result of how fast the molecules are moving. However, heat by definition is the energy flow resulting from the temperature difference, okay? So heat must involve energy flow. So let's here tackle an example here. If we have a body at 10 degrees and another body at 50 degrees, we clearly have a difference in temperature. Higher the temperature, higher the vibration of the molecules, and low the temperature, low the vibration of the molecules. So 50 degrees is moving really fast, and 10 degrees is moving slower. When we touch the two bodies, because one body has the molecules moving faster, that's going to help the cold body to get movement as well. So this difference in temperature will produce an energy flow that always flows from the hot temperature towards the cold temperature until they reach thermal equilibrium, okay? Therefore, heat is defined as this energy flow that results from the temperature difference. And always the energy flows from the hot body to the cold body until they reach the same temperature, which means they are vibrating at the same, you can call, speed. So therefore, let's think for a minute about this simple question here. Which object does have more heat? A block of ice, one system, or a flame, another system? So let's think about that for a minute. You don't need to answer me, and then we will move on. Okay, so which object does have more heat? A block of ice or a flame? Well, according to the technical definition, heat is energy flow. Okay, so nobody can have heat because heat is caused by an energy flow. So in the day-to-day, we use the heat concept in a not correct way. So therefore, none of the objects have more heat than the other one. However, if you ask about which object does have more energy, probably the flame has more energy than the block of ice because the temperature of the flame is higher than the temperature of a block of ice. Okay, therefore nobody can have heat because heat is energy flow. Okay, so I showed you the two different forms of energy, potential and kinetic. Potential energy is associated with the ability to produce work, okay? So a body at the top of the hill has a lot of potential energy to be transformed in kinetic energy that's associated with movement. Then we defined here heat, always energy flow, resulting from the temperature difference that flows from the higher towards the lower temperature until the two bodies in contact reach the thermal equilibrium. So now let's move on to the first law of the thermodynamics. The first law of the thermodynamics states that the energy has to be conserved. Okay? If a system has potential energy, this energy has to be fully transformed in kinetic energy and vice versa. We cannot lose or create energy. Energy has to be conserved. For our studies, we will define three kinds of systems. The first one is defined as an open system. An open system can exchange both matter and energy. So for example, here, if we have an open flask, that's an open system because matter can go in and out, and also energy can go in and out. Second kind of system is called closed system. Now, what we are going to do is to add a cap to our flask. And in this situation, the system can exchange only energy. Matter cannot escape the system and also not get in the system because of the cap. However, energy can flow in and out of the system through the walls. And finally, isolated system, which is a system that can exchange nothing. So in an isolated system, we cannot have exchange of matter, and we cannot have exchange of energy as well. Okay, that would be a system with a cap and a thermal insulation around the system to avoid energy flow in or out. A very simple example of an isolated system is a thermal bottle for coffee or hot water, for example. Okay, so the cap here, if kept closed, avoids matter to go in the system or flow out of the system, and the thermal insulation of the bottle avoids the energy to flow out of the system or into the system. And that's a perfect example of an isolated system. Okay, so in a chemical system, which is our interest for this chapter, the energy of the system in a given time is defined by the word enthalpy. Enthalpy symbol is a uppercase H. And remember that chemical reactions are a rearrangement of the atoms. In this process, chemical bonds are broken and new bonds are formed. Every time a chemical bond is broken, we need to provide energy to the system. And when new bonds are formed, the system will release energy because it's moving to a more stable state. Therefore, in a chemical compound, potential energy is stored in the form of chemical bonds. And this energy that any chemical compound has is defined as enthalpy. Symbol for enthalpy is H. Our goal for this chapter is to predict if a chemical reaction will absorb or release energy, and also how much energy is involved in the process, okay? So at the end of the chapter, you must be able to predict if a reaction will need to absorb or release energy when it goes all the way to the completion. And we will also be able to determine how much energy is involved in the process. And always keep in mind that chemical compounds, they store potential energy in the form of chemical bonds. To determine the flow of energy in a chemical system, we are going to use graphical representations, and those graphical representations are called energy diagrams. Energy diagrams will indicate the energy of the reagents, first thing, the energy of the products, second thing, and as a function of the time. So as the reaction progresses, we will be able to draw the energy of the reagents and products. The energy of the reagents or products is indicated by a horizontal line in the diagram. Okay, so let me show you how we are going to draw this kind of diagram. Okay, an energy diagram, the complete energy diagram, will always have a vertical axis, which is energy, and a horizontal axis, which is time. Sometimes you may find progress of the reaction in the horizontal axis, okay? So doesn't matter. The energy of reagents and products is indicated by horizontal lines in this diagram. So for example, let's imagine here a first case that we have the energy of the reagents right here, and that's our start for the reaction. Any reaction, you need to provide a little bit of energy to start the reaction. So with that, the energy of the system goes up. The amount of energy provided to start the reaction, this is called activation energy. Okay, so imagine that we moved the small sphere from the flat all the way to the top of the hill. Now the system has a lot of potential energy that will be transformed in, for example, kinetic energy and be used to produce products. And from this max point, the reaction, for example, may go all the way down here and stabilize, and that's when we form the products. Okay, so that is one case that may happen when the energy of the reagents is higher than the energy of the final products. And of course, the opposite also may happen. The second case that we may face is when the energy of the reagents is lower than the energy of the products. So let's take a look at this case. Again, energy diagram, the complete energy diagram, we will represent energy over time. energy of the reagents and products are represented by horizontal lines. So we are going to start here with reagents. Any reaction needs energy to start until gets to the max point. The amount of energy provided to the reaction is called activation energy. And from the max, then the reaction progresses all the way to form the products. And in this second case, for example, the energy of the products is higher than the energy of the reagents. And those are the two possibilities for any chemical reaction. First one, energy of the reagents is higher than the products. And second one, energy of the reagents is lower than the energy of the products. And this energy diagram that I showed you here is the complete energy diagram, which includes the activation energy and also the energy of the reagents and products. For us, we are going to use a simplified energy diagram where we eliminate the time axis and also the activation energy. So in the simplified energy diagram, what we are going to have is only the vertical axis energy, and we are only going to represent in the simplified energy diagram the energy level of reagents and energy level of products. And we are going to take out the activation energy of the system because that's not our goal in this course. So using the simplified energy diagram, we are only going to show here by horizontal lines the energy of the reagents and then the energy of the products. And then an arrow will indicate the direction of the reaction. Okay, so see here that I'm showing this line and this line, and they are going to be stacked. So in the first case, we saw that the energy of the reagents is higher than the energy of the products, and that's what I'm showing here in the simplified energy diagram. And now let's do the same thing for the other possibility. So again, simplified energy diagram, only vertical energy axis. And in this case, the energy of the reagents is lower than the energy of the products. So let's represent, again, energy of the reagents by a horizontal line, and the energy of the products, another horizontal line, and the arrow will indicate the direction of the reaction. Okay, so see here, I'm just showing this energy here and this other part here. Okay, so for us, it doesn't matter the activation energy. And we are going to use always the simplified energy diagram. Okay, so see that in the first energy diagram, we are moving towards a lower energy level from reagents to product going down. So therefore, the system is, let's say, releasing or losing energy. And in the second case, we are moving up energy levels. So that means the system needs to gain energy to become a product. Okay. So now let's try to understand when a reaction will absorb or release energy. And I'm going to do that based on the the simplified energy diagrams. Okay, so let's start here with our first reaction. So I have here sodium hydroxide, and I'm going to add water to the solid sodium hydroxide. Okay, we know from chemical reactions that when we have solid sodium hydroxide being dissolved in water, we are going to form sodium plus and hydroxide ions. Okay, and they are going to be dissolved in water. Okay, so once the solid starts to dissolve, if I touch the bottom of my system, what I will feel is that the glass tube is getting hot. Okay, so let's think about that. If the reaction is progressing and the glass test tube is getting hot, that means the reaction will progress from reagents to products in a way that energy escapes the system and is used to increase the temperature of the test tube. Okay, so that's going to be the energy flow in this first case over here. And let's draw the energy diagram for this first example. I'm going to represent energy by E. We started with reagents that I'm going to represent by R. If the test tube got hot, that means energy came out of the reaction and was used to heat up the system. Therefore, we must be moving towards a lower energy state, and that means energy was flowing from the system to the outside in the test tube. Okay, so in this first case, we are moving to a higher energy to a lower energy. Therefore, energy is being released that is being used to heat up the test tube. When we have energy released, we are going to classify this kind of reaction as exothermic. When energy is released from the system, we call this kind of chemical reaction as exothermic. And in this case, energy of the reagents is higher than the energy of the products. That means energy was released to the outside system. And we can also calculate something defined as delta H. Delta H is always the enthalpy of the products minus the enthalpy of the reagents. When we see enthalpy, that means the same thing as energy. So delta H is going to be basically the difference in energy comparing products and reagents. Okay, so in this diagram, the delta H is going to be the difference between the energy of reagents and products, and that's going to be delta H right here. If energy of the products is lower than the energy of the reagents, in this kind of reaction, the delta H has to be negative. All right, so now let's see another example here. So what I have here is ammonium chloride, and I'm going to do the same thing with ammonium chloride. Going to dissolve ammonium chloride in water. So because ammonium chloride is a soluble salt, when we dissolve the solid in water, we are going to produce ions, ammonium and chloride. And if I touch the test tube, I can feel that the test tube is cold. So that means the energy now is flowing from the test tube to the reaction, causing the test tube to get cold. Let's do here the same thing. So let's draw the energy diagram for this reaction. So in this second case, we have here again energy. Now the energy of the reagents is right here at the bottom. If the test tube got cold, means that energy was flowing from the test tube to the reaction. Okay, so the reaction needed to absorb energy to move all the way up to the products. So therefore, the energy level of the products is going to be higher than the energy level of the reagents, okay? This increase in energy, the price to be paid was that energy was flowing from the outside to the chemical reaction, and that causes energy increase. So therefore, in this kind of system, energy is absorbed when energy is absorbed, the energy level of products is higher than the energy level of reagents, and we call this kind of reaction as endothermic. Okay, so again, if the test tube got cold, that means the energy was flowing from the test tube to the reaction, causing an increase in the energy when comparing products and reagents. And again, we can determine the delta H for this reaction. Delta H is simply the energy difference between products and reagents. Okay, so again here, the delta H is simply the energy difference between products and reagents. However, different from the first case, now in the second case, when energy is absorbed, we are going to have energy of the products higher than the energy of the reagents, which will result in a delta H that is positive. Therefore, endothermic reactions, they always absorb energy, resulting in the energy of the products higher than the energy of reagents, and as a consequence, the delta H for endothermic reactions is always positive. And this is how we can use macroscopic observations to get details about the energy level of reagents and products in a chemical reaction. Okay, so using a very simple observation of system getting a higher temperature or lower temperature, we can determine what's happening with the energy of the components of the reaction. When energy is released to the outside system, we call exothermic. Delta H is always going to be negative, and the opposite case, the reaction is determined as endothermic with delta H positive, because energy is flowing from outside to the chemical reaction, to the system. Okay, to finish today, I just want to show here two examples of two chemical reactions. In the first case, we have methane, CH4 gas, reacting with water in the gas state. And this reaction will produce carbon monoxide and 3 moles of hydrogen gas. And the delta H for reaction is always going to come after the last product. And the unit for delta H is always the unit of energy, in this case here, kilojoules. And see here that we have a delta H that is positive, and the magnitude of the delta H is 206.1 kilojoules. Okay, so the goal here is to draw the energy diagram for this reaction. Okay, so how we are going to do that? The simplified energy diagram, which is what we are looking for here, has always a vertical axis, and this axis represents energy, symbol E. If the delta H is positive, that means the energy of the products has to be higher than the energy of the reagents. So let's draw that. So we are going to put here reagents, doesn't matter where in the diagram. And now that I have a reaction, I'm going to write here who are the reagents. We know that when delta H is positive, the system is moving towards a higher energy level. So let's put here an arrow, and then let's represent here the energy level of the products. And we know who are the products, so we are going to write them right here. When we measure the delta H, what we are measuring is the difference between the start and end of the reaction. And now we have the number. So let's add the number here. Plus 206.10 kilojoules. If we are moving towards a higher energy level, this kind of reaction here is classified as endothermic. Okay, so energy is flowing from the outside towards the system. Unfortunately, we don't have time to go over the second example, but as you can see, now here for this second reaction, we have a delta H that is negative. So now we just have the opposite. Okay, energy of the product, the reagents, sorry, is going to be higher than the energy of the products. The system is flowing up, down. Energy is being released from the system to the outside, and that's why the delta H is negative. And in this case, the reaction is classified as exothermic. Okay, so for now, we need to be capable of drawing the energy diagram, classifying the reaction as endothermic or exothermic, and correlate with the sign of the delta H. So at this point, I will stop, and I will see you tomorrow for the discussion section. Have a good week.
Thanks, Professor.